All right, we're going to carry on with the chapter on thyristors, specifically section 11.4, the diac and the triac. Let's mark in our textbooks again, as I've marked in mine. Introductory paragraph again. Both the diac and the triac are types of thyristors that can conduct current in both directions, bilateral. Please underline that, it's important. The difference between the two devices is that a diac has two terminals, while a triac has a third terminal, which is the gate for triggering. The diac functions basically like two parallel 4-layered diodes turned in opposite directions, and the triac functions basically like two parallel SCRs turned in opposite directions with a common gate terminal. All right, we are already familiar with the devices that we mentioned here, the 4-layer diode and the SCR. So if we go and look, there's the symbol for the diac. You have to know the symbol, of course, not the basic construction, but I can see the basic construction, or again, NPN, the bit of a different construction. And there's the characteristic curve, which you should know, of course. Now the characteristic curve, as you can see here, that's why I said it should be familiar. If I look here at this quadrant, can you see it's exactly what we've discussed in the 4-layer diode. Okay, where we've seen when I increase the forward voltage, I reach a forward breakover point, the device switches on, and it remains on as long as the anode current remains higher than the holding current. Now, but what we've read in the introductory paragraph as well is that it is a bilateral device, so it operates in the other direction as well, in the same fashion. All right, so bilateral works like a 4-layer diode, but only it's bilateral, it conducts in both directions. All right, so if we refer back to our textbooks, it's mentioned there, for the diac, diac is a two-terminal 4-layer semiconductor device thyristor that can conduct current in either direction when activated. You can notice that there are two terminals labeled A1 and A2. The top and bottom layers contain both N and P type materials. The right side of the stack can be regarded as an NPN, a PNP structure with the same characteristics as a 4-layer diode, as we've mentioned. While the left side is an inverted layer diode, a 4-layer diode having an NPN structure. Okay, the stack that they're talking about, the right side of the stack, of course, is this side, and that one is the inverted side. All right, two 4-layer diodes conducting in both directions. The equivalent circuit, remember we've discussed the equivalent circuit in the other devices as well. Consists of 4 transistors arranged as shown in figure 1126A. There they are. And we can see there that when the diode is biased as 1126B, the PNP structure from A1 to A2 provides the same operation as was described for the 4-layer diode. In the equivalent circuit, Q1 and Q2 are forward biased. And you can see here, for this section, Q1 and Q2 forward biased, Q3 and Q4 are reverse biased. The device operates on the upper portion, right-hand portion, remember the same as the normal 4-layer diode that we've discussed, of the characteristic curve in figure 1125 under this bias conditions. But of course, when the diode is biased as shown in figure 1126, C, the PNPN structure from A2 and A1 is used. In the equivalent circuit, then we can see, of course, that Q3 and Q4 will then be forward biased and Q1 and Q2 are reverse biased. Under this condition, the device operates under the lower left portion of the characteristic curve as we've seen. Yeah. So this is the lower left now. So in the one direction, on the top right, then like a normal 4-layer diode that we've discussed, and in the other condition, when it conducts in the opposite direction in the lower left quadrant. All right, that's the introduction to the triac. Let's have a look at the of the diac. Let's have a look at the triac. There's the triac, basic construction and the symbol. Of course, you have to know the symbol. Now, the triac is like a diac with a gate terminal. All right, what we've seen with a diac is like a 4-layer diode, but it conducts in both directions. Now, the SCR, we've also discussed, and this is similar to the SCR. Remember, the SCR was a 4-layer diode that had a gate terminal. So I can switch it on at any point. I don't have to increase the forward voltage until I reach the breakover voltage. I can decrease that breakover voltage with a gate. All right. Now, for this device, the triac, there's the characteristic curve which you should know. Remember, if you're ever asked to draw the characteristic curve for these devices, you have to remember to put in all the labeling, names of the axis, forward breakover voltages, holding currents, and so forth. But anyway, what I can see here is, for this quadrant, exactly the same as for the SCR that we've discussed. All right, but only we've seen that this device is bilateral, so it also does it in the opposite direction of current flow. So please remember, SCR can only conduct in one direction. Triac, of course, is bilateral. It can conduct current in both directions. Anyway, as you can see in the textbooks, triac just above figure 1127, where it says, basically a triac can be thought of simply as two SCRs connected in parallel and in opposite directions with a common gate terminal. Unlike the SCR, the triac can conduct current in either direction when it is triggered on. All right, and as we've seen with the SCR just below figure 1127, notice that the breakover potential decreases as the gate current increases, just as with the SCR. As with other thyristors, the triac ceases to conduct when the anode current drops below the specified value of holding current, IH. Remember that is very important. All right, in figure 1129, the equivalent circuit showing the transistors there again and the bilateral operation. You can see that in figure 29, the triac being triggered in both directions of conduction. In part A, terminal A1 is biased positive with respect to A2, so the triac conducts as shown when triggered by a positive pulse at the gate terminal. Transistor equivalent circuit in part B shows that Q1 and Q2 conduct when a positive trigger pulse is applied. In part C, terminal A2 is biased positive with respect to A1, so that the triac conducts as shown. In this case, Q3 and Q4 conduct as indicated in part D upon the application of the positive trigger pulse. All right, applications. On page 570, like the SCR, triacs are also used to control average power to load by the method of phase control. The triac can be triggered such that the AC power is applied to the load for a controlled portion of each half cycle. How does that differ from the SCR? The SCR, we've seen it was only half wave power control, but in this case, because it can conduct in both directions, I can see that it is for the positive and the negative alternation that the triac can do phase control. All right, so that is important. Okay, so during each positive half cycle of the AC, the triac is off for a certain interval called the delay angle, measured in degrees, and then it is triggered on and conducts current through the load for the remaining portion of the positive half cycle, called the conduction angle. Similar action of course occurs for the negative half cycle, as we've seen. All right, so that portion that we've seen over there is the same as for the SCR, but it also does the same for the negative half of my waveform, because it is a bilateral device. All right, one example of phase control using a triac is illustrated in figure 1131A. So there I can see in that circuit, diodes are used to provide the trigger pulse to the gate of the triac. Diode D1 conducts during the positive half cycle. The value of R1 sets the point on the positive half cycle at which the triac triggers. Notice that during this portion of the AC cycle, A1 and G are positive with respect to A2. And then of course diode D2 conducts during the negative half cycle. R1 sets the trigger point. Notice that during this portion of the AC cycle, A2 and G are positive with respect to A1. And then of course the resulting waveform, as we've seen in the previous figure as well. Alright, in the phase control circuit, it's necessary that the triac turn off at the end of each positive and each negative alternation of AC. So in 1132, it illustrates there that there is an interval near each zero crossing where the triac current drops below the holding value, thus turning the device off. Alright, now as we've seen here, with the diodes D1 and D2 for the positive and a negative alternation, and G, I determine where my device will switch on. But as I've just read, and I can see in the following figure, is that between those two positive and negative alternation, of course the current drops below the holding current, and the device switches off. Alright, this concludes then the diac and triac. And as normal, you should read through the section, do the relevant true false quiz, circuit action quiz, self-test. And as I've said here, you should be able to explain the basic operation of the devices with the aid of the characteristic curves and the applications discussed. But as you can see, we're not doing any basic problems, calculations in this section as well.